the unsuspecting stranger had better know the truth of wrong from right. 'Cause the eyes of the ranger are upon you. Any wrong you do, he's gonna see.
Hi everybody, we are students of the Salesian Polytechnic University, and we are going to explain to you the Laplace transform in a derivator. Here we are.
My name is Carlos Reyes.
My name is Andres Calero.
And my name is Cristian Dominguillo.
Now we are going to present to you the exposition. Okay. A derivator is a circuit in which the output signal is proportional to the time of the derivative of the input signal. In other words, the output is proportional to the speed variation of the input signal. We have here a formula that is chain of speed is the variation of the in voltage over the time. Well, there are a lot of types of input waveform. The first one that we have is the input signal is a fixed voltage. For example, we are going to consider 3 volts. So the rate of change, the input signal is 0. So therefore, the output also are going to be 0. The input signal is a square wave. Each time the signal change level, there is a sudden variation in the input signal. The input signal also can be a triangle wave. The output signal is a square. However, let the case of the square wave amplitude 3 volts is going to change from 3 to 0 volts. All the time unless of the rate change increase. The output of it jumps are reversed because the input connected to the inverting operation amplifier. The input signal is a sine wave. When the input signal is sinusoidal, the output of the wave is shown in the following graph. From this can be seen that a raper is proportional to the frequency of the input signal. The increased speed occurs when the signal crosses the horizontal axis at the step angle. Had the input noise, it could normally be a higher frequency signal to derivative comparison. This will cause little noise. Little noise bulbs appear at the output much longer. To prevent this entry is packed a resistor R1 that we are going to show in the graphic and a capacitor. And a capacitor C1 is that is in parallel with the feedback resistance R to reduce the tendency of oscillate the circuit. These latter two components R1 and C1 reduce the discharge capacity of the circuit, but only do so to frequency determining resistors and capacitors.
The Laplace transform. The Laplace transform is a widely used integral transform with many applications in physics and engineering. Denote it is linear octave of function with a real argument t more equal 0 that transforms is a function with a complex argument in the transform is essentially budget for the majority of practical users. The respective pairs of and are matched tables. The Laplace transform is related of the Fourier transform. But where the Fourier transform express a function or signal as series of modes and the average frequency. The Laplace transform resolves a function in moment, like the Fourier transform. The Laplace transform is used for solving differential and integral equations. In physics and engineering, it is used for analysis or linear time invariant systems such as electrical circuit, harmonic oscillator, optical device, and mechanical system in such inputs and outs are function of time to the frequencies domain, where the same input and output are function complex angular frequency in radian per unit time give in simple mathematical or function describe or input or output to system. The Laplace transform provides an alternative system, a new system based on set of specificities. Thank you.
Okay, the formal definition of Laplace transform. Laplace transform of a function ft, defined for all real numbers more or equal than 0, is the function fs, defined by the equation here. The parameter is a complex number with a real number sigma and omega. The meaning of the interval depends on types of function of interest. A necessary condition for existence of the interval is that f must be locally integrated on 0 to infinity. For locally integrable functions, the decay at infinity or are exponential type. The integral can be understood as a proper Laplace integral. However, for many specifications, it is necessary to regard it as a conditionally convergent improper integral at infinity. Still more generally, the integral can be understood in a weak sense, and this is dealt with below. One can define the Laplace transformation for a finite Borel measure mu by the Laplace integral. An important special case is where mu is a probability measure, or even more specifically, the Dirac delta function. In operational calculus, the Laplace transform is a measure is often treated as though the measure came from a distribution function f. In that case, to avoid potential confusion, one often writes this, where the lower limit of 0 is shorthand notation for this. His limit emphasizes that any point mass located at 0 is entirely captured by the Laplace transform. Although with the Laplace integral, it is not necessary to take such a limit. It does appear more naturally in connection with the Laplace stainless transform. Thank you.
So we are going to thank to you for your attention, and we hope that it's going to help us too. Thank you very much. See you next time.